presentations, or events or whatever. Okay, so John?
So I get to stand in for Leonard today because he's sick, but hopefully, and I do have a lot to cover, but like what Barb said, ask questions. If you have them of myself, of Bob, and also Rich, so we should get going. So I don't know if you know, but probably the biggest thing in the past couple weeks, space-wise, was that we launched a rocket. Actually, we launched a car into space. This is the most powerful rocket that we, the United States, has launched since the Saturn V, and it's all because of SpaceX. I thought about doing the video, but I found these pictures and I thought it would be a little different perspective. These are all from a guy named Ken Kramer. He's a science writer, takes a lot of photos. He's down in the Cape, based out of there, so he took these beautiful shots. I mean, they're just gorgeous. And, you know, like I said, we launched a car into space, but what you didn't know is that this is the coolest cover-up NASA's ever done, SpaceX has ever done. So I talked to Elon, he gave me his red card. They decided to put my Toyota up into space. This is real. It's a cover-up. I mean, how do you get pictures like that? So yeah, the space guy, he's in my FJ. I think we should have cleaned it. Because, you know, Elon's car is pretty spiffy, so these are the real pictures, you guys. I mean, you know, you knew that. I'm a good Photoshop guy, though.
Yeah.
The coolest part of this was the best PR thing was just double landing of the boosters. Now the big center core, it was kind of, how many people watched the launch on TV? So they gave it away. Those two announcers, like, they're talking and they're like, oh, and then they went on. It didn't land on the big drone ship. It landed about 100 meters off of it, and two of the engines didn't light when it was coming down, and so it pretty much splashed in the ocean. But that does not mean that the next time, they're supposed to have 2 more of these this year. And then, is it this week they're launching another Falcon 9 from Vandenberg? Soon they're launching another Falcon 9. These are the Falcon 9s, these little ones. The heavy is the 2 boosters and the big center core.
So John, now rather than doing spacewalks, we can do drive walks?
Drive walk?
Space drive.
Space drive.
Yeah. Oh, by the way, Elon's car was supposed to go to Mars, but they kind of overshot. Now it's going to be orbiting out into the asteroid belt and then coming back around. So a lot of people ask, what?
But it's going to that orbit, and then it's not orbiting with that asteroid.
No, it'll come back to Earth and then go back out.
Back out.
It's not, and I don't know. I guess they'll talk to it every once in a while. I don't know.
It's got nothing, it's done.
It's done.
Yeah.
So Leonard probably would have talked about this. This is the, oh man, help me with the name of this. Tiangong. Say it again.
Okay.
Tiangong.
Tiangong. That's what I thought. It's supposed to re-enter. This is China's space station. It's supposed to it's not very well controlled right now. That's what they've told the UN, although they're being pretty quiet about it. But they say it's going to re-enter sometime between March 25th and April 17th. I thought about doing this for the next meeting, but since this just came out and Leonard talked about it this week, the Chinese say this is highly variable. But, you know, the re-entry, where it's going to re-enter is everything from about the border of Canada all the way to Antarctica.
Is it totally out of control? That's why they got no fuel, they got no control, they got nothing?
They must have some control because they know it's coming down. They've been pretty forthright in telling everybody that the thing's coming down. The chances of things hitting the ground are like pretty minimal. You're more likely to get struck by lightning than be zapped by one of these pieces. I'm always winning. I'm looking to win the lottery. This will be the next best thing. I know, this is the space station. The other big news of the week was the president gave his budget proposal to the Congress or to the U.S. people. And basically, one of the biggest highlights of this is he wants to privatize this thing and make it a more of a commercial platform instead of a platform for the World International Space Organizations to do their stuff. Now, this is a worldwide effort to put this thing in orbit. The space shuttle was the big workhorse to put all the elements up into space, but right now Russia's getting all of our astronauts up there. So we work pretty, Canada built the arm on this and the space shuttle, and then ESA has done a lot too. This is the proposed budget cuts for space science. The old adage goes, what the president proposes, the Congress disposes, so we don't know where this is going to end up, but basically he wants to establish U.S. preeminence to and around and on the moon. So we've got a goal again. With Bush, it was the moon. With Obama, it was Mars. Now we're back to the moon. The request gives NASA top line budget $19.8292 billion for the 2019. And that's a bit more than 2018. Gives one of the big efforts is to move forward with creating a space station on the moon, this lunar orbital platform, the Gateway, in the 2020s. And then, so it gave money to do that, and also landing, but not manned landing. This is all robotic. Wants to partner with commercial space companies to do more stuff, and proposes to end some ISS funding, doing a commercial real estate venture. Planetary spending, though, planetary science spending was not really touched. Actually, it's going to increase. So that's a good thing. But these are some eliminations that he's proposed, that they put in the proposal. Cutting 5 Earth science missions because we don't need any more Earth science stuff. They want to gut the education office at the NASA. Seems kind of strange to me given the PR value of that. And plus it's my job. Well, not my, I work for Education and Public Outreach with the National Solar Observatory, which is part of the National Science Foundation, but we're like this, hit to sometimes. What's that?
NASA and National Science Foundation are in the same budget.
They're not in the same budget, but a lot of times it just trickles down. There's a lot of cross-pollination between the two.
Okay.
They're really pretty separate.
Well, they are pretty separate.
There's some things that are like some people do planetary astronomy, like the telescopes. They can get funded from NASA or NSF, but the money goes to one or the other.
They are pretty separate that way, but I'm talking from a PR standpoint. A lot of people think NSF, they think NASA when they think NSF. So anyway, one of the biggest eliminations is that they're talking about is the WFIRST. WFIRST is going to be looking at dark energy, exoplanet stuff. It hasn't been launched. It's way over budget. It's just been, I don't know what's been going on with it, frankly.
It's behind James Webb, which already went way over budget, right? I mean,
Right.
It's another giant telescope that it's the top priority for astrophysics. They really want it, but I think everybody's just tired of JWST.
So James Webb, it's the next Hubble, is going to launch later this year. Well, it's been packed up to go along. Another thing Leonard talked about this week was space warfare, new threat assessment. Daniel Coates, the director of national intelligence, presented this to the U.S. Everybody, and what's funny is that back in the 80s when I was going to college, I wrote this paper for it was a government class or something, and talked about Star Wars, the old, anti-satellite, all this stuff, laser weapons in space, and I got an F on that paper because the guy said it was it was sci-fi. I'm like, don't you watch the news? And I gave him all these sources. Nope, got an F because it was science fiction.
I should have given you an A for originality.
But anyway, so this Daniel Coates went into the NS satellite efforts that China and Russia have been going on, the operational forces. There was talk earlier this year of having a space corps, right? China and Russia have been thinking about the same kind of thing, a Marine Corps up in space. Directed energy weapons, these are lasers and other mass projectile stuff. And experimental satellites, such as the little space shuttle that the Pentagon sends up and has to go around the Earth for 600 days. So that Leonard talks about all the time. You remember this thing? It's not wrong. Oumuamua is the name of this thing. I can't hardly remember the name of it. Oumuamua. This is a rock that came in from interstellar space, zipped by us and went out. The reason it's back in the news is that it didn't come and stop and send signals or anything, doggone it, but they've done a lot of studies because it's such a special thing, and it looks like it's just been through hell. I mean, it is more battered than it should be. And so these scientists, they did some studies, and let's see if I can get this thing to go. I don't know, I've talked about it in the past, but, oh shoot. It rolls end over end in this just wild sort of gyration. And, yeah, I know, pretty cool. That's not real, that's another Photoshop job that I've done. No. And then this one. Ooh, there's sound. This shows the orbit of it. Now, when it came through and how it diverted it, the sun diverted it.
How big is it?
I think it's 6 kilometers long. Not very big around. And so look how fast this thing is moving along. This is the orbit of Jupiter. And it's 2019, 2020. The thing is looking. I mean, and it also has on one side of it has a sort of a orange reddish tint to it. A lot of the exoplanets, a lot of bodies we have out in the Kuiper Belt have this from methane with ultraviolet light. When it reacts to it, it turns this reddish color. It's only red on one side or in parts of it, and so again, they think it collided with a huge body wherever it was, wherever it originated. And that started its tumbling, and then it got ejected out of its solar system, and eventually it ended up here, and then it's leaving. So, again, anybody remember what this is?
Pale blue dot.
Pale blue dot. This picture was taken back in 1990.
Voyager?
What's that?
Voyager, right?
It was Voyager.
Outside Pluto.
Way outside the orbit of Pluto. Voyager 2 took this image. That's Earth from way beyond the orbit of Pluto. Carl Sagan wanted to take this picture really bad. Excuse me. He called this the pale blue dot, and it became a documentary and a call for action for humanity and stuff. But this little guy right here, New Horizons, which went to Pluto, is now 6.12 billion kilometers, that's 3.7 billion miles, 40.9 astronomical units. That's the distance between the Earth and the Sun. It's now slightly farther than the pale blue dot image that is snapped in 1990, and it took this picture. So now this is what's the name of this cluster? I forgot.
Where's the Earth?
It's not in the picture. What was significant about this picture, this was a calibration picture that New Horizons took, I think probably to break the record of the pale blue dot image, but this was also the very first image that was taken by the Hubble, this cluster. I can't remember the name of it. Doggone it. But it also turned around and took pictures of the next objects it's going to encounter. And so, it was the first to encounter Pluto. It made the most distant course correction maneuver, which just took place in December. And now it's taken the farthest planetary pictures, pictures from out there. So that's kind of cool. Moving along really quick here now. This week, as of February 1st, hear much about, this is Gaia. This thing is trying to do a 3D model of the universe, cataloging billions and billions and billions of stars. One of the cool things it found this past couple weeks is that Sirius, the very bright star here in the night in the sky, right to the south here, part of Canis Major. There's a cluster of stars behind it. It's so bright that we don't see it, but Gaia caught it. So I thought that was kind of cool to point out. This is our big guy on Mars, Curiosity. Took a selfie. Mount Sharp is in the background. That's where it's ultimately trying to get to.
Where's the arm then if it took a selfie?
They,
Where's the outside?
No, it's
Well-
it's many individual frames that it takes, and so when it's taking a picture over here, the arm's just not in the picture. Then over here with the arm, take a picture over here, the arm's just not in the picture. So
They
by the
put
time
it
they
together.
mosaic them all, there's just never an arm.
yeah. So in a way, they Photoshop it out, but yeah, there's enough. Photoshop is everywhere. But boy, it's been getting these really close. It's got this camera called Molly, looking at these minerals that probably were formed in the presence of water. Bob knows much more about all this than I do. But I just think it's fascinating. These are not big images. These are like looking as far away from the surface. So these are sand grains down here, not big boulders. Anyway, who's next? You guys have questions? Questions? I gotta get him up. Told you I'm doing double duty.
This is the magic toy here.
That is it.
Which one do you push to go forward?
Backwards, forwards.
Okay, what do the other ones do?
Stop.
Disappear?
Those are the don't push these buttons, Rich buttons.
Yes.
It'll come up in a second. Come on. There it goes.
There.
Okay. Guess I'm on here. Okay, I originally titled this talk 2 Centuries of Volcanic Aerosols Derived from blah, blah, blah. But then in the last minute moment, I figured Moon Over Maui sounded nicer, so it's called Moon Over Maui. And I'm probably one of the few people on planet Earth that get paid to go places to observe lunar eclipses. Everybody and their uncle goes to see solar eclipses and even asteroid occultations and all sorts of obscure astronomical phenomena. But lunar eclipses I have all to myself. Okay, so my basic project is, whoops, all right, that's the wrong button. Here we go.
Point at this.
Yeah, I'm the director and sole proprietor and only member of an experiment called the Lunar Aerosol Climate Experiment, or, you know, in good NASA-ese, I have a acronym for it, lunacy. And the purpose of it is to, in a nutshell, derive and measure the amount of volcanic dust in the upper atmosphere from observing lunar eclipses. And it can be done, it's not new science. A guy named Johannes Kepler figured this out about 400 years ago. Okay, and the money, some of it comes from my own pocket. No drug deals go into this or anything, mostly from my own pocket, or from a grant from the University of Colorado Retired Faculty Association, which actually for me is very pleasing because when I was actual faculty, I did a lousy job getting grants and funding. I just wasn't good at the game. But now that I'm retired, I excel. So I'm getting these grants to go, and yeah, no animal students or retired faculty were harmed. So, okay, so in a nutshell, the science of this is, a lunar eclipse is when the moon goes into the shadow of the Earth. Here's the Earth, the sun is way over there where the streetlights are out in the parking lot. So the shadow of the Earth is cast on the moon. However, the shadow itself is not completely dark because light is bent by the Earth's atmosphere into the shadow. So on its way to the moon, the light is bent into the shadow, but it spreads out and gets dimmer, and also it gets redder by passing through the atmosphere. If you ever watch the sunset, that's exactly what's going on. The light's going through all this atmosphere and it gets redder and redder because the blue light is scattered out. So what happens when the moon is in the shadow? The moon turns red, but it also gets darker than a normal full moon by a factor of several thousand. Okay, and here's another diagram that goes into detail on it. and there's the moon smiling at you. But the science is, if you put dust in the atmosphere, it blocks the light from going into the moon, so the moon is darker. So if I can calculate how much dimmer the moon is when it's observed during an eclipse, compare that to what it would have been had the sky been clear, the difference is due to volcanoes, I can backtrack and come up with a number for how much volcanic dust is up there. So it's actually quite simple, pretty elegant, and the computations are dreadful. I mean, actually calculating all these paths of light is, believe me, I did that about 30 years ago, and I don't ever want to do it again.
Okay, question.
Yeah,
So
question.
you're looking at the dust in our atmosphere, or the dust in our atmosphere and cosmic dust, or just cosmic dust?
It's mostly dust in the stratosphere of the Earth. Let me go back. Of course, the stratosphere is the next layer. We're in the troposphere. Okay, top of the troposphere is 30,000 feet, 40,000, or something like that. Then it's the stratosphere. That's where this stuff hangs out because of the nature of volcanoes. It blows the stuff up. A big volcano, mind you. Little ones, no. But big ones put stuff into the stratosphere. Stuff that goes into the troposphere falls out. It mixes with clouds, it becomes rain, falls to the ground. It's gone within days. Like Mount St. Helens put up almost a cubic mile of ash, pulverized rock. But most of it fell down within a few hours. Some of it lasted a day. It actually fell in Colorado, but it was all gone within a week. And none of it got up in the stratosphere. So the stuff that goes up, by the way, this will be significant. I think Bob may have something to say about this. The material that actually goes up in the stratosphere is sulfur dioxide from volcanoes, goes up into the stratosphere, and on Earth it mixes with water vapor, makes little drops of sulfuric acid, which becomes the haze that does the dimming of the moon. Okay, so, and here's a comparison with and without, and again, this is not new science. This is from 1884, observation of eclipse a year after the big eruption of Krakatoa in Indonesia, and it was very dark, very colorless. It was not a nice bright red, orange moon. But then 4 years later, after the stuff settled out, here's a normal one. And these are chromolithographs, so it's not a photo, it's a drawing. It's the observer's impression. But again, it's from almost a century and a half ago. So, but the effect is astounding. This eclipse here could be 1,000 times dimmer than this one here. It's a big effect. It's easy to observe. So, here's the eclipse when was it? 2 weeks ago, January 31st, in the wee hours of the morning. So I had this little grant to go somewhere to observe it. Well, where to observe it? Well, first of all, you want to go someplace where the eclipse is above the horizon. So, from Colorado perspective, Colorado was not good because it was already getting low in the sky when it became total. The twilight was beginning, and so conditions were not ideal here. And also, it turns out it was cloudy. So, of course, I didn't know that beforehand. But, so I knew I wanted to go west somewhere to where, like in this white area, the entire eclipse would be visible, be higher in the sky, and it'd be in a dark sky, not a twilight sky. So I can further narrow it down by looking at maps of global cloud cover. So here's a map of global cloud cover. Here's Colorado. You can see, actually, Colorado, never mind the 330 sunny days a year, Colorado is actually cloudy. All seasons of the year, Colorado, especially the high country, is cloudy. Not like Buffalo, New York, or Juneau, Alaska, but in terms of the continent of the 48 states, it's one of the cloudier places. So Colorado is really not the great place for this. So the least energy route would be Arizona, and we got relatives there who'd be glad to host us. And the sky be somewhat darker, the eclipse would be marginally higher in the sky, but that was too mundane. North Pole would be perfect, the moon would be up, the sky likely to be clear, but it's really hard to get there in January. The flakes there are seasonal, so not for that. My pick place was Nuku Hiva. How many people have heard of Nuku Hiva? Okay, it's in the Marquesas Islands. To get there, you fly, you go to Papeete, Tahiti. And there you grab a once every other week steamer that goes up through the Tuamotu Islands and jump overboard and go snorkeling on the way. And it's a fun trip. And ends up in the Marquesas Islands and then comes back. And my dream was to take that trip and be up there. However, the schedule did not permit it. The day of the eclipse, it was back in port in Papeete, Tahiti, and that was not a good spot because this green band is one of these tropical convergence zones that's rainy. So it's dry season in Nuka Hiva, but rainy season in Tahiti. So scratch that, that left Maui. No other place in the world would do it. So there's Maui. So booked the flight to Maui, and the other option was the Big Island, which is, well, we were just there a couple of years ago, so I figured Maui for a change. So, I mean, even though totality was an hour and 20 minutes, we booked 9 days just to cover it. Okay, so here's Maui. Beautiful place, shaped like a peanut. They call it the Valley Island, I call it the Peanut Island. And it's got, well, actually, a lot of things make it a good observing spot. If I go back here, you can see climatologically it's relatively clear. Not always, you can expect it to be clear, and weather is what you get. So weather does happen. Keep that in mind. We did find that out. But a lot of times the clouds there are low clouds, so you can go up the mountain to the top of Haleakala and observe from above the clouds. Or if the winds are coming from one way and the clouds are on this side of the island, you go over to that side. If the winds are from this way and it's cloudy here, you go over to this side. So being a fairly small compact island, you've got a lot of options for maneuvering and optimizing the terrain and getting to hopefully a clear spot which has a very good chance of existing somewhere on the island. So meteorologically and eclipse-wise, it was a good spot. And also, it's a fun place to be. So we stayed at this bed and breakfast. It was up in the hills, a place called Kula, which is kind of central, and roads going in all directions, so had the mobility. And again, it was a beautiful spot. So first thing you do when you go to Maui is go up the mountain, and the mountain's cool, Haleakala. There's this landscape there. I guess I'd call that a lunar landscape. A lot of telescopes up there. I didn't need telescopes for my observations. Actually, they were done mostly with naked eye and with a pair of binoculars turned the wrong way. And I'm serious about that. I really needed very minimal equipment to observe this. And yeah, okay, so it looks like the moon in that photograph, but there you go. Kind of looks like Mars on this. Question is, Mars or Maui? This is the summit of Haleakala. And the only photoshopping was making the sky pink instead of blue. Otherwise, you couldn't tell where that was, I bet. I mean, I picked up the beer cans in the ravine, so you really can't tell where this would be. And I've never been anywhere on Earth that reminded me more of Mars. And my memories of Mars are profound. Okay, what else do you do? Well, one, you eat the food. You can have manapua, which is like a Hawaiian pierogi, which is proof that Hawaii was settled by Poles who were trying to sail to Duluth and got caught in a storm and blew around the horn and ended up in Hawaii. So, manapua, it's like a dumpling. It has pork and pineapple and good stuff in it. Helen, my lovely bride there, she likes musubi, and especially the Span musubi. When we arrived there craving it, we went to Foodland, which is the local King Soopers, and they were out. But we went back the next morning and got some. So, and musubi, by the way, is rice with Spam on it wrapped in seaweed. So, it's up to you to do value judgment on that one. Okay, what else do you do? You can go snorkeling in Molokini, which is, I think it is the smallest of the Hawaiian Islands. It's a submerged and decayed fraction of a volcanic cone. Half of it's gone. The boats take you out there. You can charter or get on a snorkel trip and go out there and go snorkeling there. It's really nice, although my impression was the reefs have suffered from love. Too many people go out there and look at it and, Yeah, so it's not as nice as it was 40 years ago. Or go out whale watching, that was a hoot. We went on a trip out there the first day and saw a bunch of whales around like a half-mile away. Liked it so much, 3 days later went out again, and the whales were an eighth of a mile away. And pretty good thrill seeing whales. And there were lots of them. It wasn't like one or two. It was a whole herd or a flock or a gaggle, whatever whales are. A pod, yes, right. Open the pod bay doors. Okay, so the whale watching. So that's what you do in Maui when you're waiting for the eclipse. So then the eclipse arrives. Well, so did a cold front. You know, what's a cold front doing in Hawaii? It's supposed to be up in Alaska or Colorado. So that's Big Island, that's Maui, cold front coming in. Not good news. And here's the satellite picture leading up to the eclipse. Big Island, Maui, and there's the cold front. Well, in the hours right before the eclipse, the front was breaking up, it was dissipating, the clouds were thinning, but would it thin enough for Maui to be clear during the eclipse? Well, the short answer was no. So the eclipse began 2:52 a.m. It was overcast. Matter of fact, partial eclipse began, it was overcast. Mid-eclipse, 3:30 a.m., it was overcast. And we're observing from Kula, from the bed and breakfast, being a convenient spot. But I could notice at 3:30, way down to the south, there were some stars appearing. So made the decision, hop in the car and drive south, which was doable. There was a road headed south for about 10 miles. So we hopped in the car, headed south, and here's the satellite picture at that time. There is the southern tip of Maui, the southern eighth of the island. Now, Big Island was in Fat City, but Big Island's there and we weren't, so that's irrelevant. So there is the southern bit of Maui. So the trip was, here's the Peanut, number 37 is the road name, but it's very close where the Kula View bed and breakfast is. Hopped in the car, drove, couldn't have been more than 15 minutes, got down here, and Helen was looking out the window, looking up, and I was trying to stay on the road. Yeah, it's out in the open. Oh, okay, screech, pull over and so on and see it. And so we parked on the access road to the hospital, and fortunately there were no admissions at 4 in the morning there, and saw the last 20 minutes of the eclipse. Beautiful. And there it is. So there's the last, this is total, like last minute of total, minute and the partial, the sun is starting to shine there, and then some of the increasing partial phases. So we just had an absolutely gorgeous view of the eclipse. You know, it was for 20 minutes instead of an hour and 20 minutes, but, you know, the solar eclipse is 2 minutes, so, you know, still ahead of the game on that. So again, quite beautiful eclipse. Well, I didn't go there to take pictures. Remember, I went there to do science, to make observations. So I made my observations of the eclipse. And how do you observe the brightness of a lunar eclipse? Well, okay, there's the sky over Kula, Hawaii during the eclipse. There's the moon, and there's a bunch of stars around it. So what you do is you look up at the moon and compare its brightness to the stars surrounding it. You know, like Regulus and Procyon and Castor and Pollux, you know, some of the brighter stars in the sky that are near the moon. However, there's a glitch. The moon tends to be quite a bit bigger and brighter than the stars, even when it's eclipsed. So what you need to do is to find some way to shrink the moon down to make it look like a point, like a star, and also make it dimmer so its brightness is in the same range as the stars. Compare the two, and then knowing how much you shrunk the moon down, apply that factor to fatten the moon's brightness back up to what it really was. Does that make sense? Yes. Okay, so the way I do it is I have a little spotting telescope. Looking through this backward little telescope and looking, oh, the moon was like Regulus, or the moon was like Pollux, or, you know, comparing it to the stars, and actually got some good observations of it during the last 20 minutes of the eclipse.
Why don't you use a CCD and just take a picture?
Okay, because part of the reason I'm doing this is comparing it to the historic record, which goes back to 1800. Actually, it goes back to Kepler, 1604, who observed an eclipse the same way.
So he used,
And continuity in geophysical measurements, long-term ones, is really important.
so he used the same technique.
Yeah, yeah. Yeah, nothing new here.
Nothing new under the sun.
Yeah. I mean, you know, why change what he did? He did it well, so yeah. I'm not gonna better him. But fortunately, yeah, I caught the last 20 minutes, but several other people on the West Coast were able to catch the earlier parts. Now, people from North America, from the mainland watching it, they could catch the early phases if it was clear, but then it got low and sank into the fog or behind the mountains or blah, blah, blah. And like, this guy here is in British Columbia. Place guaranteed to be socked in during the eclipse. Well, like he had a 10-minute break during the middle of the eclipse, so he got a nice data point. And John Westfall, he was out in the Bay Area, California. Fred Espenak was in southern Arizona, and they all got good observations. So between the four of us, we had the whole thing covered. So what is plotted here, the dots, the big moon-colored dots, are the individual observations made by the four observers. The red curve is a polynomial fit to it. You know, there's a bit of scatter here, but sort of a best guess curve as to what the observations really would have been if there was no error bars and so on. And then the blue is the predicted that I made based on a clear atmosphere. So the bottom line is the red line and the blue line are not that different, which means there was not a whole lot of volcanic stuff up in the atmosphere at the time of this eclipse. Now, what the eclipse is measuring is not just volcanic stuff in one spot. It's all around the globe, because light from all, I'd say corners, but the Earth really is round, okay? You know, from all parts of the spherical Earth being bent into the shadow. So it's really a global sampling. Well, you know, that wasn't a guarantee, because in the past year, 3 of these big eruptions, Fuego in Guatemala, Agung in Indonesia, and Mayon in the Philippines, all of which have been catastrophic eruptors in the past, killing thousands of people. You know, these are big, dangerous volcanoes, and they all erupted in the past year, you know, quite beautifully so. But their eruptions were not big enough to really put a lot of stuff in the stratosphere. So in terms of the volcanic dust surrounding the Earth and the climate impacts of it, these things, even though spectacular, gorgeous, they really had no effect in the upper atmosphere.
So Richard, why does John, Richard,
Rich,
right?
yeah.
Why does the visual magnitude change with time, with clock time?
Oh, okay, that's a great question, I'll go back to that one. Okay, because this is when the eclipse begins, the moon is right at the edge of the shadow. As it progresses, it gets deeper and deeper into the shadow.
So that's the total eclipse where your finger is right now.
Yeah,
Okay.
that would be so this would be the brightness of the eclipse when it begins, and then it gets into the middle of the shadow, it's darker, and you can see that during the eclipse itself, one side of the moon, the side towards the edge of the shadow, is brighter, usually, than the part towards the center of the shadow. They're quite a bit darker. So,
Got it.
yeah. Okay, so this is my 200-year record, and basically this is a data point from Maui, and it's a continuation of the other data points for the past 25 years, which means it's the longest volcanic drought on record this past 20, since Pinatubo. In terms of the stratosphere, in terms of stuff in the stratosphere where there's enough to impact the climate, that is, you know, the longest volcano-free period in history. You know, you could argue maybe back in here too, but you know, there was this one in the middle there. But the eclipse coverage wasn't quite as complete. And again, the whole history of this I find fascinating. You know, volcanoes don't occur just, every 10 years. They're kind of random. And you had this 110-year period from Krakatoa to Pinatubo when there was actually a lot of significant eruptions. None since, and very few before, except for the mother of all volcanoes in terms of historical context, which is Tambora in the Philippines, which was many times bigger than anything ever since, probably 10 times more stuff in the atmosphere. And that one had a distinct effect on the climate. The Year Without a Summer, 1816. And some people have even blamed this eruption for the writing of Frankenstein, because Mary Shelley was in Geneva and commented on how gloomy the summer it was and got her in the mood to write this book about this beast. And the gloomy summer was a direct offspring of Tambora. So there you
So are
go.
we due?
Unexpected effects of volcanoes.
Are we due for volcanoes? Can you go into the future?
Question was, are we due and can we go into the future? I can't. No. No, I mean, I attempted to predict the weather a few days in advance. I'm okay at it. And I've tried predicting tornadoes like 10 minutes in advance and gotten pretty good at that. But predicting volcanoes, no. I'll leave that to the soothsayers. Okay, next lunar eclipse, Turkey, making plans to get over there. January 2019, a year from now, there's one visible right here. Prime time, high in the sky. No need to go anywhere else, unless it's cloudy. Yeah. And then lunar eclipses take a break, and then we have a few years of solar eclipses. You know, Chile, that one actually, in my plans to go to Tahiti and then catch a boat south. But you could go Chile, Argentina. Same, 2021, actually I forget where it is.
Antarctica.
Oh, yeah, Antarctica. 2023, it's the west coast of Australia. Okay,
And 2024, back to the United States.
Austin, Texas.
okay. Yeah, somewhere, Buffalo, New York. I mean, yeah, if you want to get away from the clouds, go to Buffalo. Okay, so I'm going to end, and this picture is kind of a segue. Back in 1978, I was a reporter for the Miami Herald. My beat was space and hurricanes, and space beat was, the both beats were kind of a lot of fun. So I got to observe the Pioneer Venus launch, which I believe is the last U.S. mission to land on Venus. Right?
Yes.
Yes,
Well, they
1978.
weren't planning on landing, they just happened to touch down and survive.
Yeah. That was 40 years ago since we've been serious about Venus. Okay.
But the Russians landed many times after that.
Okay, and actually I had a lot of other fun things with the job. When I was up there for the launch, being a reporter, NASA loves reporters, gave me the VIP tour, and I got to stand in the fire pit of Pad 39, where the flames from all the Apollos, most of the space shuttles, and the Falcon 9 touched down.
Wow.
You know, the pit, where the flames came down. And this was in the flame bucket where they put the gazillion gallons of water right beforehand and so on. That was a real hoot. That was in that 6-year period between Apollo-Soyuz and Space Shuttle 1, when they didn't have any launches there. And they're actually, being in Florida, you leave something unattended for 6 weeks or 6 years, it's a jungle. It looked like a Mayan temple. We were just covered with vegetation, which they then cleared off for the space shuttle and put it back to use. And down here's a little graph I found, and it's sulfur dioxide in the atmosphere of Venus, but it's actually measuring the exact same thing I measured in the previous graph, which is sulfur dioxide in your stratosphere, and very similar effects, like Venus has episodic volcanic eruptions. But maybe not. I don't know.
It's
Yeah,
one of two
okay.
ideas.
But anyway, so this is the segue into the next speaker. From Earth to Venus.
Thank you, Rich. Yes, okay. You can pass the clicker on to Bob. So yeah, I think we're so privileged here to have, and he's a geophysicist with the Southwest Research Institute in Boulder and a 21-year Coal Creek Canyon resident. And he's a very close friend of all of ours. And I'll let him get into this because I know this is, you know, we've got a lot of information we're giving you here. But yeah, we're just honored to have so many people up here who are experts and can give us these presentations. Okay, sure.
Thank you for coming. It's been a very great program already so far tonight. And I'm going to have to move faster than I had anticipated. So I naturally talk fast. I'll try to talk loud and fast. Maybe that would like deliver all the information. I'm a geophysicist, a planetary scientist. Barb mentioned I've given 3 other talks, but you know, Venus is my first planet, and I'm in a position now of sort of helping shepherd what the United States plans are for Venus exploration, and so it just seems like a good time to talk about this, mainly because of the lack of exploration of Venus that we've done in recent decades. This is a picture I just grabbed off the web of Venus in a telescope. We always have to remember, you know, what our roots are and what this really looks like. But the takeaway thoughts that I want you to have from this talk today is that we call Venus Earth's twin because it's nearest in the solar system. It's the nearest planet to us. It's about the same size as the Earth. It's made of more or less the same stuff, rock and metal. But it evolved very differently, both in its atmosphere and its surface. And we don't understand completely why. This is a basic question of what we call comparative planetology. How do 2 planets behave differently? Back when the Magellan mission was going on in the early 1990s, I was a postdoc, and I think probably the only time I've been interviewed on TV, you know, they said, what do you think about Venus? And I said, well, it's like, you know, you put 2 pies in the oven, they come out differently. You think it's the same pie, but it's not. Well, something changed, something had to have changed. But what is it that's different that made those 2 pies come out differently? And so not only for understanding, you know, how our own solar system works, but with this explosion of exoplanets, I forgot the number John quoted, 3,000 or something now, you know, only some fraction of them are the size of Earth or Venus. But how do we know when we look out there which ones are going to be Earth-like and which ones are going to be Venus-like? So the whole world of exoplanets has sort of put a point on the reasons we need to understand Venus. Now, Venus was the first planet ever explored by an interplanetary spacecraft, 1962. We'll hear more about that later. But since the 2000s, only 2 spacecraft have visited, one from Europe and one from Japan, none from the US. And NASA has basically abandoned Venus as an exploration target. We'll talk about some of those reasons why later. So here's the deep background on this story. This is, I think, about 1992 or so. I was a postdoc. This is Roger Phillips. He was my advisor. With me in this picture is Susan McCarr. She's been at JPL for many years and may very well likely lead the next Venus mission. And Robbie Herrick, a longtime friend who's a researcher in Alaska. When I was very young, I didn't know what I wanted to do, dinosaurs or space. I picked space. And when I realized, wandering around the library as an undergraduate, that you could actually learn about what's inside a planet from the outside. You didn't have to drill it. You could use gravity and seismology and other methods to understand the inside of the planet from the outside is what really hooked me. And this question occurred to me back then. Why are Earth and Venus different? So I spent half of my PhD studying Venus, the other half studying asteroids. The 1990s came along. Venus, once the mission I was working on, Magellan, was over, NASA cut the research funding after that too. There were some diehard people who kept working, but by the late 1990s I moved on to Mars and the Earth. But since the late 2000s I got involved with Robbie and some other people in writing mission proposals. So we wrote a couple of radar mission proposals to go back to Venus. I've been trying to send a balloon to Venus. And then recently I'm the chairman of this group called the Venus Exploration and Analysis Group that advises NASA on what they should be doing for Venus. And the short answer is anything. So let's start over with Venus. What's the basic things we understand about it? It's the brightest thing that you can see in the sky. It's visible either in the morning or in the evening. Does anybody know where it is right now? It's
Evening.
it's in the evening, but I couldn't see it tonight, it's too close to the sun. The sky map says you can see it, but maybe if you're at sea, you could, the horizon's totally flat. I couldn't see it tonight. Galileo discovered that it shows phases, and the fact that it never gets far from the sun in the sky, and then it shows phases says that it goes around the sun, and the Earth is outside of it, which is the heliocentric theory. Now there is a geometric alternative to this, but once you started trying to find ways of adding forces to this is really the only way that works. So Venus was pivotal in understanding the structure of the solar system. A guy named Lomonosov discovered the atmosphere of Venus in 1761 when there was a transit of Venus when it goes across the sun. He noticed that the light was bent around the atmosphere, kind of, I guess, backwards in the geometry that Rich just talked about. So that goes back quite a while, the discovery of the atmosphere. In the early part of this century, a guy named Arrhenius, who's very famous in chemistry, calculated the surface temperature of Venus to be over 100 degrees. And they knew it was an atmosphere, so this is where this idea of Venus as a swampy planet, possibly with life, predominated throughout most of the 20th century. It wasn't until the 1950s when people started making radio telescope observations so the radio telescope tells you the temperature in this temperature range, and they derived a temperature of over 600 degrees. Now, this is the telescope they use. It's at the Naval Research Lab. These are not the people who did it, but this telescope is still there. And so they found this temperature was over 600 degrees. Well, they couldn't decide at that time whether it was some funky space physics thing from the ionosphere, electron precipitation or something, or was it just Venus that hot at the surface? A young, I don't know if he's a graduate student or a postdoc, must be a graduate student, as I wrote a dissertation, named Carl Sagan, worked on the idea that Venus could be a runaway greenhouse. The solar energy is trapped, and the planet heats up because of the massive atmosphere. So he worked on this, and they thought, okay, Venus is probably hot and dry, and not a swamp. But we can't just look at it as a point in a wiggle from a radio telescope. We need to get up close and take a picture of the whole disk. And it turns out there's technical reasons about how the variation of the temperature across the disk would distinguish between the two hypotheses. Was it from the high up in the ionosphere, or was it from the surface? So that was the genesis of the first interplanetary spacecraft from the United States, Mariner 2. And they used a microwave radiometer to show that, in fact, that this was from the surface. Now, what happened to Mariner 1? Well, we're very fortunate tonight to have a guest. So if you want to step up here, this is Richard Kate. And he was an engineer at JPL at this time and worked on Mariner 1. And so we're going to hear a short rocket story.
Well, yeah, I'm an engineer, okay, and so I'm one of the guys that makes the tools and the instruments and the cameras and the spacecraft to allow these guys to collect data to write their PhDs with. At the same time, they're the guys that make the case as to why we should go to Venus so that I can build something to go there and get the data. Okay, but what I'd like to try to quickly do here is give you some idea of how complicated this all is, and how, when you see what we're doing today, it's just so, even for me as an engineer, just sort of mind-boggling. When a guy lands a rocket that he just spent in a place on a platform in Florida, I mean, it just blows me away. But let me give you some idea of just how complicated and how tricky all this stuff can be. The Mariner 1 spacecraft got blown up. We intentionally blew it up. And the reason we intentionally blew it up is we thought it was out of control, because it was out of control, okay? Why was it out of control? What happened? Well, who of you mathematicians in here would like to tell me what it means when I take a variable like x and I put a bar over it? What's that mean?
Average.
Average, okay? What I want you to do is I want you to average the value x. I don't want to know the instantaneous value of x, I want to know the average of x, okay? X in this case was the gyro rates. And so, I don't know for any of you that have ridden on a gyro, or not a gyro, but any of you that have ridden on a rocket, you know it's a pretty hard ride. And so the gyros are doing this, okay? The gyros are bouncing up and down, but the average of that bouncing up and down is kind of like zero, which is kind of where you want to be, okay? Well, when the computer programmer wrote the program to take these equations and control this missile, he didn't see, forgot, screwed up somehow, and ignored the bar. He ignored a simple little thing like the bar. And instead of the computer looking at the average, it looked at the instantaneous. As it looked at the instantaneous rates from these gyros, which are hopping all over the place, because that's what they do, the control system tried to correct the rocket for what it thought was something wrong. So now the rocket, instead of doing this, is starting to do this. And the range safety officer, whose career is on the line, if that rocket hits somebody on Earth, he's done, okay? He sees that rocket going crazy, he pushes the destruct button, and that's what happened. We blew it up. So a half of an $18 million in 1960 dollars ended up in the bottom of the Atlantic because somebody forgot to recognize the bar on the equation.
How long afterwards did Mariner 2 launch that they could fix that?
Within just a few weeks, because that launch window is a window. There's a certain time of the year that you can go to these planets. You can't go just any old time, okay? There's what we call a launch window. So within a couple of weeks, in fact, there were a lot of stories that come out about what happened, and if you would go way back to one of the headlines for this thing, the people in the press, bar didn't mean a lot to anybody in the press, but they knew what hyphen was. And so the headlines were, spacecraft lost due to a hyphen. So anyhow, so just to give you an idea of just how complicated this stuff can be.
And this was the first time ever,
Yeah,
right? So
yeah, it was the first planetary mission that we ever did. We did it in less than a year for $18 million, and a team of about 20 plus of us designed it, fabricated it, launched it, flew it. And now there's a launch team, a design team, a software team, a control team, you name it. So, it was fun.
great stuff.
Yeah, it was fun.
So back then, I mean, NASA always, and the Russians too, launched it, everything was a pair. It was always two rockets, two spacecraft, two of everything. And we quit doing that, I think about after Viking. So by the mid, and Voyager. So by the launches in the 1980s and beyond have all been just one-off launches. In cases of the Mars program, you know, we've lost spacecraft. So the Mariners, coolest name ever too, by the way. There was a series of them. Some went to Mars, some went to Venus. This is sort of the classical picture that I grew up with of Venus, which is in the ultraviolet. And you look at Venus in the visible, it's completely bland. You can't really see anything. But in the ultraviolet, you can see these details of the cloud tops. The Russians had an extremely successful Venus program, starting in the 60s. Their real successes came in the 70s and 80s. Why do you think they started so vigorously in the 1960s? I mean, they could have started at any time, I guess, but the late 1960s.
We beat them to the moon.
That's exactly it. By the late 1960s, it was obvious that we were going to get to the moon first. The Russians had failed in their giant booster that they needed to send a single-man lander, and so they turned their attention to robotic exploration of Venus mostly. I like to think of the Soviet Union was a second world country with a giant army and a great space program, a Venus program, because they landed many spacecraft. Well, Venera 8, 9, 10, 11, 12, 13, 14, Vega 1, 2. So that's 9 spacecraft they landed on the surface of Venus. They only lasted about an hour or so. They made huge engineering efforts to keep it cool enough to make measurements. But you know, they took chemical measurements, they took atmospheric measurements, and these pictures at the bottom, I'm going to guess and see if this is a laser pointer. It doesn't work on the screen anyway. These are the original pictures, and you know, you can see some kind of bumpiness on the horizon. There's this guy named Don Mitchell who has reprocessed all these, you know, into sort of an orthorectified version, and it looks like they landed quite close to some ridge belts on Venus. We'll see what these look like in radar from space later, but you know, that's the surface of Venus, volcanic rocks in this location, some weathering and dirt. So that, you know, very successful program. We saw the night launch of Pioneer Venus from Rich's picture. This was a great mission, 2 spacecraft. One, the bus sent 4 probes in the atmosphere, one of which, survived on the surface for a short amount of time. So I guess that counts as a U.S. landing, but these spacecraft weren't designed for that. The other one was a radar orbiter, and also made atmospheric measurements that provide the first global map of the surface of Venus, at least in terms of its topography. There weren't very good pictures at that time. The big breakthrough that when my career started was with Venera 15 and 16 and Magellan. So all the previous Venera, which means Venus, spacecraft had been atmospheric or landers. The Russians went for an orbiter this time with a synthetic aperture radar. So this was a relatively new kind of radar that was started in the 70s. It's where you not only look off to the side, but you use the motion of your platform to sort of squeeze the beam down and get a much bigger picture. These were developed for military purposes, but there's actually a big explosion now with small satellites, these little CubeSats and stuff. People are actually trying to deploy radars now on them because there's lots of applications seeing through clouds and seeing what people are doing. So you have to use this radar to see through the clouds of Venus, see the surface. And this is just a part of what the Russians produced in the mid-'80s. And I worked on this for parts of my PhD. This is Maximo Montes. It's a big mountain belt. These are big mountain ranges. This is a hugely deformed region, crunched up. This little dot here in the middle is called Cleopatra. It was called Patera back then. It's about 100 kilometers, 60 miles across. So this is, thousands of miles on the side. This was thought to be a volcano, but it turned out to be an impact crater. This is a Magellan. You see much better resolution, 10 times better, and the shape of the way that these mountains are around it, how it forms around the circle, perfect circle, suggests it's an impact crater. And this blew me away because you get this tallest mountain range on Venus with a crater sitting on top of it. And that means it probably didn't happen yesterday, geologically speaking. And that changed my thinking about Venus. I'll come back to that later when other things were going on. So that's Magellan. It was launched from the space shuttle because they thought the space shuttle could do everything back then, instead of just sticking with real rockets. The 2 most recent, Magellan ended in 1984. The 2 most recent missions to Venus was one by the Europeans, that was called Venus Express, and another mission called Akatsuki, that is Japan's. They're an up-and-coming space nation now with interplanetary missions, asteroid missions, Mars missions, and they've got this thing in orbit around Venus. This is the most amazing space story in robotic exploration because their main motor, their chemical rocket, exploded when they tried to enter Venus orbit. It didn't ruin the spacecraft, but it blew up the motor and it wouldn't work anymore. So they sailed past Venus, around the sun, and the engineers got to work. And years later they came back, and just with the little thrusters, little attitude rockets, they managed to burn those long and hard enough to barely get captured in orbit around Venus. So it's a pretty terrible orbit. It's super elliptical. It takes like 2 weeks for it to go around Venus. It comes in very close. That's how you get captured, by flying very close to a planet. But then it loops way, 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 way out. But it's still taking pictures of Venus. And as a matter of fact, we'll just take a little interlude now to look at some pictures from Akatsuki. These were processed by a so-called amateur, and the Planetary Society saw them, and they recruited like 3 scientists to comment on them, just because they're so cool. So I'm not going to get a lot of science here. These are really ooh-ah pictures. So this is Venus. So this amateur, using Photoshop or whatever, has combined, just like Sam does with his astrophotography pictures, has combined the different bands and assigned different colors to them. So here we see this classical view of Venus where you see this Y-shaped feature, that the sun is over here. It's always kind of around the position where the sun is. All the winds are screaming around this way. These are the main clouds, and then he's got these polar regions. Here you can see, this is the South Pole, I think, yeah. And look at all these little instabilities that are forming along that as those layers are shearing past each other. Maybe Rich has a more technical comment on this. Here is another ultraviolet composite in which you can see a lot of sort of more small-scale modeling, and that's indicating that there's vertical motion, so there's convection happening. I don't know if you would call these cumulus clouds necessarily, but I think they're kind of analogous. This one best shows, this is in the infrared, I use the same colors, but these brighter areas are where the heat from the lower atmosphere is getting through more, and then these are cloudier areas where it's purple that are masking it. So you see a lot of pretty sharp demarcations between different parts of the atmosphere. And this was my favorite. I don't really know what this is. They said, is it correlated with topography? And I look at this, and this looks like Aphrodite Terra, which is one of the big continental masses, size masses on Venus. And so, it's known that, I'll show you later, a giant scale structure, gravity wave that was launched from this area. So maybe we're seeing smaller scale interactions with the topography. So Akatsuki is turning out to be a very exciting mission. So, all right, let's start off and talk about the planet, kind of by process now, and not just missions that have gone there. So it orbits